means these are the power supply that are supplying through the socket of the IBM PC, okay, through this socket. Then I have another power supply from the top here that comes from inside here. I have a fan that are removable hot swap, as it is called, and also the power supply is redundant, so the fan and the power supply are calculated to dissipate up to 30 watt per board. Okay. Now this is the way the board has been that I designed and introduced all this. There are, as I said, 20,000 pins, so design one by one all these components. These are the components of the communication connector. So after having introduced this data, and this is the daisy chain, for instance, all these big components, the 28 components, the big one, they have a TDO, TDI chain, daisy chain, serial line, that I can test the connection and functionality of each chip just by running a program that goes through the daisy chain. And this is the circuit of the, let me see, let's use this one. Okay, so typical circuit of with a lot of components. After having done this, I use the tool, I say package, and it takes about 13-14 minutes to package, means to create a database, and this database, it will be used by this other program, that is the program of the layout, physical layout. And the one that keeps track, for instance, here I can show one layer at a time. So now I am showing the surface layer, excuse me, this one from this side here. Okay, then I can show these are the power supply, this is the ground, and one layer of ground, but there are several layers. This is another layer. Let me turn off the previous one so you can see a little better. So you see the one was vertical and horizontal. This is more horizontal. The one interesting is this one, because it's the one that is distributing the clock. Let me zoom a little bit here. Okay. So you see that there is a serpentine because it's equal distance. So I am getting the clock here. It goes there. It goes to this 4 chip in the middle. And then from this chip, equal distance goes to all the destination. So I can have a director of orchestra that gives the time to all orchestra, and everybody starts, and the tolerance that I can achieve with this technique, with all the components that I put, is 40 picoseconds between any component in any chassis, even different chassis in different place. I can tune it to 40 picoseconds. And this on semiconductor and well. So these are the characteristics of the board. If there are any questions, otherwise I think that we take a break for lunch. And we are exactly on time, I think. Yeah. Is that right? Yes. So are there any questions? You cannot see the audience because we are working here, so if there are some, we will take it afterwards, okay?
Okay.
So we will adjourn to 1 o'clock?
1 o'clock Central Time.
Central Time. Half an hour, 30 minutes from now. Okay. Collected for a certain time at a given energy. Now, we have a source here, a radioactive source. By the way, I have measured, and everybody must feel safe, and Jerry also can witness that. He gave me the instrument, and I measure during also the past days to just make sure that we are not in a dangerous situation. The result of the measurement were for, I think, 12 hours, putting the measurement device 1 less than 1 inch from the source, just on the box, I was getting in 12 hours what 5 milliamp, and at 5 inches it was not moving, it was nothing. Okay? So it's I also calculated is emitting 170,000 disintegration per second. Single photon is a cesium 137, and comparison. Remember the 370 million per second. This is 170,000, so we can stand that. It's a little more than the radiation from the sky. Anyway, although you look from this graph that there is a characteristic emission at 661 kiloelectron volt, we have emission from zero to that energy, more or less, but still energy. So if we look at the oscilloscope, this is what it shows. We show a fluctuation, a random of photons at different energies. The duration is 200 nanoseconds per square, is about 1.5, one square. So that is what we are looking for, and that is the task is to identify, discriminate, measure very well the photons that we are interested in, discharge on the others. So, given that, with this electronic, this photomultiplier, now this was built here in the area, and there is a 4-channel, so it's a very well-known technology for the preamplifier and also the constant fraction discriminator that is triggering on the same time, independent from the amplitude of the signal. Okay. So again, one more, I thank Photonis. They sent me the size of the photomultiplier, 16 of these 4x4 will fit on this crystal that I got from Saint-Gobain. And also, to complete the chain, now I got also the 16 power supply from Caen in Italy. Okay, can we move to the...
Now, I guess the question I'm asking is, does a pair of devices, a pair of events that are time units, do they determine just a line through your machine, or does it also determine a distance along that line? You're not using the time difference.
No.
That is pretty sharp.
No, it's not precise. The time of flight. There has been some detector measuring the time of flight, but there are two kind of technique. One is called assistance, and the other one is trying to determine where along the line you got the hit, okay, and that is the time of flight. Assistance is the one that just you try to have a time measurement to set a window, to discriminate from photons from other events. And that is my goal.
So then the final imaging algorithm just takes all these various determined lines and sees where they pile up.
Yes, where there is an intersection. Because you can imagine the time of flight, the electronic is to be an electronic of the order of 50 picosecond resolution in order to get a reasonable resolution.